Hello. Hey, Amin. Hello, Pika Pika. Yellow Ando Bear. Hey, Jack. I played an unhealthy amount of Beat Saber this weekend. That's the VR one, right? I think I'd be good at that game. Lightsaber skills. What are you playing it on? Are you playing it on like the Oculus or the Vive, or what's going on? It's so much fun, and you can download custom songs. Hey, good afternoon, everybody. Good afternoon, Chinghan. That guy who stinks says, "Aye!" VR is really sweet. I want to play Half-Life Alyx. Hey, Brandon, how are you doing? Hello, Nyquist. Perseverance landing on Mars in 3 days. Ooh. Now, what's the nature of the Perseverance mission? Are they making first contact? Hey, hello, Belkit. Hello, Nyquist. Hello, Kate. There's a YouTube video of a guy doing math lecture in Half-Life Alyx. I've seen this. That's really good. There's a glass window and a marker you can draw with. Yeah, I really want to play that game. Mike says Perseverance is trying to find life at the bottom of a dried up lake and flying a drone. Do you guys think that there's life on Mars? And do you think it is sentient life? I wish I can play any game continuously. There are assignments with weekend deadline. Assignments get in the way. You bet. Kate bets there was sentient life at some point. Mark says, yeah, Matt Damon is there. Matt Damon. Microbial life, probably. I love Matt Damon as an astronaut. But then their atmosphere got blown off. Big sad. Well, maybe they should have protected their atmosphere if they cared so much about it. If they really enjoyed being sentient beings. Solar radiation go burr. Some theorists think it's our ancestors who sent DNA from Mars to... No, what you're thinking of is the Prometheus film, the Alien movies prequel, Belkit. That's what you're thinking of. They weren't Chads about it? What does that mean? Okay, let's get started here. Ancestors equals microbial life on meteorites from a big impact. Oh! I thought you meant future, like futuristic, technologically advanced ancestors. All right. It's Monday, week 3. Week 3 of 15, I guess. No breaks whatsoever. Actually, we'll take some breaks. We'll take a day here or there. Happy Monday, Nikta. Am I in the wrong room? No, you are in the right room. You're in the right room. But we're going to talk about digital controls today. Let's do a quick recap on where we are. Right now we're talking about the relationship between continuous time roots and discrete time roots. And this is the relationship. If you have a continuous time root, let's call it lambda sub c for continuous. This is the relationship to a discrete time root. Wait, I did this wrong. It's e to the continuous time root times your sampling period. All right. Why do we care about the relationship between discrete time and continuous time roots? Well, when we actually implement a digital control system, we're going to do it using difference equations. When you write your code on the Arduino, it's going to be a difference equation. So in practice, we operate in this domain over here. But when we're talking about I need to turn the music down a little bit, I think, here. But when we talk about performance specifications for when we are designing the control system in the first place, usually those performance specifications are specified in the continuous domain. T is the sampling rate, or the T is the capital T is the sampling period. It's the time between samples. All right, so we're going to start over here in the continuous domain with performance specifications, and then depending on our hardware, like what's our sampling rate, we're going to go over to that discrete domain. So the first thing we're going to do today is we came up with this relationship when we were looking at real roots, purely real. And I want to know, does this relationship hold up if we have complex roots? Like if the continuous roots are complex conjugates, can I still use this formula? The answer is yes, but let's see why. We're going to do an example. So consider this homogeneous differential equation. So this is a continuous time system. It's second order because it has a second order derivative here. And so it has to have two initial conditions, and I actually only listed one over here. So let's give the second initial condition. I'm going to specify x dot at time 0, and I'm going to set it equal to 0. So now we're good to go. We have two initial conditions. And these next couple parts, we're just going to zip through really quick. So the characteristic equation for this continuous system, let's put like lambda c for continuous. So lambda c squared plus 4 lambda c plus 43.4784 equals 0. All right. And then you solve this quadratic equation for the continuous time roots. And this is what we're going to get. Minus 2 plus or minus 2 pi I. So it's complex conjugate. This is a stable continuous system. Remember, there's different rules for stability for continuous versus discrete systems. If this was a discrete time root, it would be an unstable root. But for continuous time systems, if the real part of the root is negative, then you're stable. So this is stable. And let's just break these apart into like the first root and the second root, because I'll use this later. So we'll just call the first one the positive complex conjugate, and we'll call the second one the minus. All right. If you solve for the homogeneous solution, you use the initial conditions and everything. This is what you're going to get. X as a function of time is going to be e to the minus 2t cosine 2 pi t. So what does it look like if we have t on this axis, x of t on this axis? It's going to decay because of this exponential out in front. So I'm going to draw a decaying exponential envelope. A little bumpy. That's okay. And it's a cosine, so it's gonna start up here at 1, and the oscillations are going to be bounded by this envelope. So that's what the response looks like. Oh, a little vocabulary here. The imaginary part of a continuous time root is called the damped natural frequency of the system. Damped natural frequency, and the symbol we like to use is omega sub d for damped. So the d doesn't mean discrete here, it means damped, and that's not a w, it's an omega. Okay, there's a difference. There's a swoop in here. Notice the swoop. Okay, so let's say this is some real life system that behaves in this way. There's lots of oscillatory systems in nature. If you went outside right now and pushed a tree branch, it would kind of swing back and forth a little bit. Don't push it too hard, you could break it. So let's say it models some physical system in nature, but we're going to use some hardware and we're going to sample the dynamics at discrete points in time, separated by a time duration t. So let's do that. So I'm going to put little tick marks on here that represents when we actually get a measurement from this system. Let's put one at time 0 as well. So we're going to get one like here, 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 here. And this is all the computer's seeing. It doesn't see the pink line underneath, it just sees these dots. All right. So let's write out what these samples are on our computer. So at our first sample, time 0, we're going to use this formula and just plug in the times to get this. So at time 0, it's going to be e to the 0 cosine 0, which is 1. So we already knew that. The initial condition is 1. So if we sample at 1, it's going to be 1. And then we're going to sample some time later t. So this is like the second sample we get. And so because in this case we know the underlying function, I know that this is what the amplitude of the sample should be. And then let's go down the line some point until we get to the kth sample. So at kt, which we generally just call this xk. Why is there no sine term in the homogeneous solution? That just happened because of these initial conditions that I specified here. If the position variable is 1 and the velocity variable is 0 at initial time, then it'll just revert to a cosine. All right, so this is going to be e to the minus 2 kt cosine 2 pi kt. So I know that this function describes my sampled amplitudes explicitly as a function of k. So I want to relate this to what I know, what the homogeneous solution. What am I saying? Okay, I'm just going to write it first. I'm going to try to say it. We know that the homogeneous solution follows a form like this. You have some amplitude times a discrete root to the k. And I know this is going to be a second order system. Like, if you have a second order continuous time system, it converts to a second order discrete time system. Like, the order won't change. So I know that this is going to have two discrete time roots. And I can generally write it like this. And my goal here is I'm going to try to relate this form to this form over here. So I'm going to set these two equal. E to the minus 2 kt cosine 2 pi kt. And what this is going to let us do, it's going to let us solve for what are these discrete system roots, lambda d1 and lambda d2. And I want to relate it to the continuous. And we already know what the relationship should be. It's this one. That exponential relationship, but we're going to make sure. Okay, so what I'm going to do is I'm going to expand out this expression on the right. So this is using some variation of the Euler identity right here. You can write a cosine in terms of complex exponentials like this. 1/2 e to the 2 pi kt I plus e to the minus 2 pi kt I. So that's just rewriting the cosine. And now I'm going to expand this out. So I could rewrite this as 1/2 e to the, and I'm gonna combine like these because I'm gonna multiply these terms together. Minus 2 plus 2 pi I t to the k, and then I'm also gonna have this term e to the minus 2 pi I times t, and that thing to the k. So that's just rewriting the line above. Like, I'm multiplying out terms, reorganizing a little bit. But now you see it looks like that form over there. So I got a1, and then in here, this argument is lambda d1. And then we got that power to the k. This is a2. And then in here is lambda d2. So let's write this out. So lambda d1 is e to the minus 2 plus 2 pi I times t. And lambda d2 is e to the minus 2 pi I, all of that multiplied by our sampling period t. And if you scroll up a little bit, you'll see that that is indeed lambda c1 and that is lambda c2. So now we're very happy because this relationship, lambda d is e to the lambda c times the sampling period. Now we've confirmed this works for real continuous roots, complex continuous roots. If you give me any variety of continuous root, I can transform to the corresponding discrete time root using this formula. Now this is kind of cool. We mentioned last time that if I have how do you calculate e to the I? You mean like get a number? I would convert it back to probably a cosine and a sine. Like, complex exponentials are always weird to look at. Like, what does it mean? It's an imaginary number. So the Euler identity is a nice way of like going back and forth and making some sense of it. Okay, so there can be many discrete time roots that represent one continuous root because we could have many different sampling periods. Maybe I'm sampling a system at 100 times per second, 200 times per second. Maybe I have a very slow computer. I'm only doing 10 times per second. So what this over here is representing, this is the complex plane here. So I have my imaginary axis, I have my real axis, and I'm showing where the discrete roots go depending on the sampling period. So up here, this one I'm only sampling 10 times, or I'm sampling once every 10 seconds. And so the root's very close to the origin. Actually, I think I have something in Matlab. Let's see here. Let's see if I can get this going. Let's go over to Matlab really quick. Okay, I want to go... I think I just want to run this. Okay, we got to skip forward a couple times. Once more. Okay. This is what our continuous system looks like. It started at 1, and then it did like a couple oscillations. So now let's sample it. This is sampling it. What is this? The time period is a millisecond between samples. So if I like zoom in here, you'll see that there's actually just like many, many, many samples. So this, from this perspective, each sample, it looks like the signal isn't changing very much. So that's why when we're sampling so quickly, the root is very close to this stability boundary. It's like, it almost looks like marginal stability. T. Jackson says, I don't remember, was the settling time the time required to reach 98%? Yeah, we usually use 98% for settling time. Okay, and basically, as we sample faster and faster, the response is going to decay more with each sample. And the faster, the less steps it takes for a discrete time system to decay, the closer the root gets to the origin. All right, let me see where this code goes. Basically, this is just updating when we're sampling. So if we sample once every 0.1 seconds, that's going to be the green here. And so it's going to be changing kind of significantly in between samples. Let's just keep going for a second. Okay. This is something interesting here. If you look at, let me explain this. Maybe I'll erase some of this. It doesn't look like there's a clear trend for how the discrete time roots change with the sampling period. I mean, except that the faster we, or the slower that we sample, the magnitude of the roots generally gets smaller and the roots move towards the origin. But what's up with this root up here? So this is kind of just an interesting trend to show, but as you sample slower and slower with this system, the discrete time roots follow this weird spirally pattern in the complex plane. And it just goes more and more and more. Fibonacci, I don't know. Da Vinci Code, I don't know. Tom Hanks, I don't know. But very interesting. We're going to... this shape we won't get into too much detail about, but there are other interesting shapes in the complex plane for discrete time systems that we will dissect a little bit more. Okay. Let's go to the next page. It's easier to talk about the discrete time roots and their position in the complex plane in terms of magnitude and phase. So now I want to get between these next two pages of notes, we're going to get a nice clean expression for the magnitude and phase of a discrete time root. Okay, so let's say we have a generic complex conjugate. That's another word for underdamped, or underdamped is another word for complex conjugate. So let's say we have this pair of continuous roots. We have the damped natural frequency, and then sigma is just the real part. And we know sigma needs to be negative in order for that system to be stable. So the discrete time root, lambda d, it's going to be e to the lambda c t. And then if we plug in that root here, sigma plus or minus omega d I t, we could write this as e to the sigma t, e to the plus or minus omega d I t. And then if I use the Euler identity, depending on the plus or the minus here, you always have this cosine term, and then it'll be plus or minus I sine omega d t. And let's break this clearly into the real and imaginary parts. So this cosine part goes with the real, and then this sine part goes with the imaginary. All right. I'll leave this here for a second because I know I wrote really fast. And we have to go to the next page next. I don't know why I reserved so much space on this page, whereas on other pages, it's super cramped. More space to... oh my goodness. To draw a pug. Needs lots of wrinkles, right? All right, we're almost done with this. Okay, good. Okay, good. Okay, so what we showed on the previous page is if you have a continuous root like this, the discrete root, if you break it into the real and imaginary part, help me. Yeah, that's what that pug is saying. Oh my goodness. Okay, let's say we throw this root. I'm just going to make up the positive conjugate here. But I know that whatever continuous root this corresponds to, so the real part here that magnitude is e to the sigma t cosine omega d t. And then this amplitude of the imaginary part would be e to the sigma t sine omega d t. All right, so I just plopped some discrete root into the complex plane. I put it inside the unit circle here, so it's a stable root. And then I just separated its real and imaginary parts into these expressions, which I know relate it to some underlying continuous. Would it have the I as well? No, I'm not using the I because this just represents the actual length, I guess. There's probably a better way to say that. What am I trying to say? Like this is like you can think of it as a unit vector. Yes, Pika said that very well. Indicating that it is in the imaginary axis. Yeah, I like that. Like if you're doing dynamics and you break something, like this is along the x unit vector direction, or it's along this body vector direction. So this is just along the imaginary axis direction. Thank you, Pika. All right, so let's write this position in terms of magnitude and phase. So first we're just going to do this mathematically. So the magnitude is the square root of the real component squared. So e to the sigma t omega dt, that's just the real component. We square it. And here we have the imaginary component, and we won't include the I here because it's just the component along the imaginary direction, so there's no I in there. We square that. If you work this out, you know, both of these share this exponential term. So I could pull that to the side. I squared it and I factored it out. And then I have cosine squared omega dt plus sine squared omega dt. And we know that cosine squared plus sine squared of the same thing just goes to 1. So that term goes away. And we're just left with, when we take the square root, this simple expression for the magnitude of the root. E to the sigma times t, where sigma is just the real part of the continuous root, which will usually be a negative number. So geometrically, the magnitude is just the distance from the origin. So that distance is e to the sigma times your sampling period, t. All right, let's get the phase. And that is just this angle in here, which I've generally been calling it theta. But you could also write it this way. You have like this angle symbol, and you put the root in there tucked into the corner. So this is the inverse tangent of the imaginary part of the discrete root. So that's e to the sigma t sine omega dt divided by e to the sigma t cosine omega dt. So that's how we get that angle in there. So you'll notice the e to the sigma t just cancels between the numerator and the denominator. And so you're left with this sine over cosine, but that's just the tangent of omega dt. So I have the tangent inverse of the tangent of omega dt. So this also just gives us something pretty straightforward. It's just omega dt. So maybe we'll put this over here and kind of box it. If we're given a continuous time root, we can immediately figure out what the magnitude of the discrete time root would be. And what the phase angle would be. And this angle is in radians, by the way. Okay. All right, we're going to go to one more example here. Okay, let's just go into it. Damped natural frequency. Oh, what is omega d again? Yep, damped natural frequency. Thank you, T. Jackson. So, I want to talk about this frequency a little bit and how it relates in the continuous and discrete domains. And this is interesting, like, because we're starting to talk about sampling signals, there's a concept of signal aliasing, which is, we'll get into it, but this is something that happens, oh man, I'm having trouble finding the right words today. Do you guys ever have days like that where you just forget what things are called? Okay, we'll get into aliasing though. We'll explain what it is. I can relate. I'm glad you guys can relate. Okay. We'll get it. We'll get to it. But let's start here. Consider a pair of continuous time roots. So we'll call them lambda c. And so we've been using this kind of notation. Sigma for the real part. That has to be negative for it to be stable. Plus or minus omega d, which is the damped natural frequency. But let's define the real part to just be -1/2. But I want to leave the damped natural frequency variable. So we're going to change the damped natural frequency a little bit and see how that affects the discrete time root. Let's go down to the bottom really quick. I want to draw another complex plane. But this is going to be for the continuous time roots. And the one on the right is going to be for the discrete time roots. That's why this one on the right has the circle. All right, so this pair of continuous roots that we're looking at, I'm fixing the real part to -1/2 here, right? But so let's throw this pair of continuous roots here. So the imaginary part, that amplitude for both the positive and negative conjugate, that amplitude is omega d. So just imagine with this continuous time root, we're going to kind of like move this up and down a little bit. Okay, so that's what we're doing with the continuous time roots. So now let's talk about the discrete time roots. So we know that this formula is pure gold. E to the lambda ct. It works for complex roots, real roots, whatever. So it's our good friend now. And we're going to assume this, that no matter what the damped natural frequency is of this continuous time system, we're going to keep our sampling period to 0.01 seconds. That means we're going to sample this system, take a measurement every hundredth of a second. So this implies that the sampling frequency is 100 times per second. That's 100 hertz. But we like to write this in radians per second often. So that's 2 pi times that sampling frequency. So that would be 200 pi radians per second. All right, so just we've fixed the sampling frequency here. So we just talked about magnitude and phase. Let's first calculate the magnitude of these discrete time roots. So we have this formula. The magnitude is just e to the real part of the root times your sampling period. So that's e to the minus 1/2, because that's the real part of the root. And then our sampling period is 0.01 seconds. And this is 0.995. And notice, this is not a function of the damped natural frequency. That means no matter how fast I sample this system, the magnitude of the root is 0.99. Or wait. No matter how fast the damped natural frequency is, sorry. The magnitude of the root is always 0.995. So let's go back to our drawing over here, but let's go to the discrete time plane. So this means that I'm going to draw like a dotted line, a distance 0.995 from the origin. Because no matter what the damped natural frequency is of the continuous time roots, the discrete time roots will always be on this dotted line somewhere. All right. Now let's talk about the phase. So we have this formula as well. The phase angle, so like the angle we make with the positive real axis, is omega d times the sampling period. Says, what is omega s? So fs, we call this the sampling frequency. And omega s, you could also call that the sampling frequency. The only difference between fs and omega s is the units we use to express that sampling frequency. So 100 times a second or 200 pi radians per second. It's just our sampling rate. Okay. So, okay, this is going to be the phase. So this does change with the damped natural frequency of the underlying system. So we could plug in the 0.01 here, but I'm going to write this a little differently. So the sampling period, t, is equal to 1 over the sampling frequency in hertz. Or if I do it in radians per second, it's this relationship. Okay. The reason I'm writing it out in this way, wait, let's write it just like this. It's because this ratio of the oscillation frequency of the actual system, omega d, the ratio of that to how quickly you're sampling is important. Let's make a table. I guess we'll put this table down here. And what I'm going to do is we're going to try a bunch of different damped natural frequencies. And we're going to look at how the phase angle of the discrete root changes. Okay. So the first one we're going to do is imagine the damped natural frequency is 0. Well, if I do omega d times t, okay, this would be 0. So this first root, ooh, actually, we have to make a little system here because, actually, let's do the next one first. Omega d, 25 pi. So 25 pi radians per second. I picked this for a special reason. This is 1/8 of the sampling frequency in radians per second. So the underlying system dynamics that we're going to sample, that's 1/8 the frequency that we're actually sampling. If it is stable in continuous time, doesn't that imply it will be stable in discrete time? Yes. Yes, it does. And the phase of the positive conjugate root, if you do this, I'm going to do this in 2 different colors. What colors do I want to use? Okay. We're going to do red for the positive conjugate root. And we're going to do like this lime green for the negative conjugate. Let me just show you this. So we know we're going to get 2 roots. The positive conjugate is going to be up here. It's going to be on this dotted line because we know the magnitude of all these roots, no matter what, it's going to be on that dotted line. But the angle here, is that 2.5 or 25? It's 25. So this angle is pi over 4. The negative conjugate, say these will come in pairs. This will be minus pi over 4. So these are where the 2 roots are going to be. Let's just keep going with this table for a bit. Let's double the damped natural frequency. So now we're going to make it 50 pi, which makes it a quarter of the sampling rate. All right. So now these roots, the positive conjugate is going to be up here with a phase angle of pi over 2, so 90 degrees. And these always mirror each other about that real axis. So the negative conjugate is going to be down here. Okay. And then let's keep going a little bit because there's a cool trend that happens here. So we go to 100 pi. That's the sampling frequency over 2. So I'm doubling it again. And now the angle is going to be pi. Actually, for the positive conjugate and the negative conjugate. So we're kind of like, as we increase the frequency of the underlying system that we're sampling, the discrete roots have been like moving around the outside of the circle this direction. And now, look where they are. The red and the green are right on top of each other. And they're on the negative real axis. Do you remember what the response of roots on the negative real axis looks like? It's going to be like a sawtooth. Something like this. Okay, just keep that in your mind. And we're going to keep going. Let's increase to 150 pi, which is 3/4 of the sampling frequency. Now the angle is 3 pi over 2. Oh, wait. Let's break this into colors again. It's going to be 3 pi over 2 for the positive conjugate and minus 3 pi over 2. And this is where aliasing comes in. You might not have ever seen aliasing in this way. So we're sampling a system. We increase the frequency of the underlying system. The roots are moving this way. And now, if I move 3 pi over 2 for the positive conjugate, it comes down here. So that's 3 pi over 2. And the negative conjugate root, well, now it's like up there. And notice, these roots are in the same place that they were for this sampling frequency. Like, roots are in the same place. It's just like, I guess two of the roots switch places. But if you just simulate a discrete time system with two roots in this position, it doesn't really matter. You have two roots in this position, and the dynamics are going to look exactly the same. I think I have a figure here. Oops. I'm going to pull this up. I know we're running over time a little bit. Wait, where are you? Ooh, okay. Okay. Let me explain what's going on here really quick. Look at this continuous red line first, all right? So it has some frequency. It's a continuous system. Now, next, look at this dotted green line. Hopefully that shows up for you. It's not like a crazy bright color. But this is another continuous system. And it just has a higher frequency. So it has more cycles per second. Now, look at these dots here. There's these red circles and there's these green squares. These are happening at my words. Oh yeah, you can see that these are happening at 0.01 second intervals. So all of these dots are evenly spaced. So we're sampling the red line and the green line at the same frequency. Like I'm taking a sample every 0.01 seconds. But notice, in both of these cases, if you sample the red line or the green line at 0.01 second intervals, the sample points are going to end up at the same place. Even though we know that the underlying systems are totally different. And so what's happening here in terms of like discrete time roots is the underlying frequency is making it so that the discrete time roots for those sample points end up in the same position. And so the discrete time system, just those dots, it behaves the same. And so the trend here is the roots move this way. For increasing frequency. But there's a limit, which is over here. Because if you are taking samples for something that goes beyond, and so I think this line over here is half of your sampling frequency. And this is where the Nyquist theorem comes in. Because if you have some dynamics that are faster, if the frequency of the underlying dynamics is faster than half of your sampling frequency, you're going to get this aliasing phenomena, which just means that you're sampling, the discrete time system looks like something else. My words are getting jumbled up today. But so we'll probably come back to this another, because this will keep coming up. So we don't only have one shot to explain this, but whereas with a continuous system you can just like keep increasing the frequency and getting a different system, there's like a ceiling for a discrete time system, and the ceiling is set by your sampling rate. The fastest frequency you can get with a discrete time system is like this sawtooth pattern. And that happens over here with a phase angle of pi. And I feel like I'm starting to talk crazy, so we're just going to stop it right here, okay? The important thing to walk away with today is this relationship for discrete time and continuous time roots, magnitude, phase. Those are the big ones. So we should never go beyond sampling frequency over 2. Correct. I mean, if you're running an experiment and you want to characterize some dynamic system, you need to make sure that your sampling rate is at least 2 times faster than any oscillation dynamics that are happening in the real physical system that you're monitoring. Yeah, I might want to come back and just do a lecture just focusing on aliasing and like draw some pictures to explain it too. But even that rule, typically we want to sample much faster than that. Like if you want to, like say there's like a real sinusoid and I want to sample it, you probably want to sample 10 times or so per cycle so that the dots will actually recreate some semblance of the shape underneath. If you only sample this like 2 times, it's going to look terrible. This relates to why propellers of planes start to warp when you video record them. Yes. Yeah, like if you're taking a video 60 hertz or something, if the propellers, wait, so how fast do the propeller have to be spinning for a 60 hertz video when we start to see some warping? has to be greater than the sampling frequency over 2. Okay, so I mean, that's just like if the propeller's going around 30 times per second, right? Then your 60 hertz video can start to have some aliasing. It's very interesting. No, that's because the camera scans from the top down, so the prop moves while the picture's being taken. Oh. All right, everybody. That wraps it up for today. Wednesday. What are we doing Wednesday? Wednesday, we're going to start going into defining performance specifications for a controller. That's the starting point of designing a controller, defining the performance specifications. Those performance specs will be related to continuous time routes, and then we'll convert those to discrete time routes. Settling time, yes. So tomorrow we start talking about settling time, overshoot percent, rise time, peak time. The next homework I'll either post today or tomorrow, and it won't be due on Friday. It'll be due next week sometime. Thank God, LOL. Yes. Yeah, it won't be due Friday. Don't worry. Hey, thank you, Cowardly Bean. I appreciate you guys. Hey, have a fantastic Monday. Have a fantastic Monday, you guys. Hope you're feeling good. Thank you, Pika. Stay safe. Oh yeah, there's a winter storm that's brewing. I guess like it's going tonight until tomorrow afternoon. Be safe out there, guys. 7 to 14 inches of snow. Man. Get your soup on, says Kate. Oh, JP, some really good skiing. For those of you into the winter sports, this is your chance. They got snow in freaking Dallas, says Amin. Yeah, that's... I heard they have like a state of emergency. Something about living in JP, you're at Holiday Valley right now. Kudos to you. Taking online learning to the next level. Living in Buffalo, I'm impressed with how we handle snow. Like Texas, they have to shut down everything when it snows. Hey, Quarone, thank you. Buffalo, we keep the everything running. Schools in Buffalo don't even close. Yeah. Yeah. They haven't heard of salt down there. That's what I heard. Yeah. Yeah. Yeah, they don't have the equipment. I mean, I guess, like, if you only get a storm like this every 30 or 40 years, yeah, you don't need to invest in that infrastructure. Hey, have a good one, JP. That's true. I'm from Fort Worth, and we had snow like once every couple years, and usually just some dusting. Okay. But now you're getting like feet of snow. Jeez. Even you can find people jogging. Hey, dude, I've been jogging. Even in this weather. I've realized it's possible. Because you heat up so much. My COVID pool tested negative. That's good news. You rode your bike to campus to print out notes, didn't die. Well done. Well done. Wait, I have a question for you guys. Because I don't understand how this works. So at UB, we have the COVID surveillance testing, right? And they test us in groups. But how do they find out our individual results? Is it like they mix all the samples from like 10 people into one sample and just see if there's any COVID in that mega sample? But then how do they break it into individual stuff? If the pool tests positive, they go back and retest the individuals. Wait, so you have to go back again for another test? Well, they keep part of the sample just in case. That makes sense. No, that's efficient. That's very efficient, right? Okay. That makes sense. Your pool tested positive. Yeah, I've seen that come up a couple times with different people. Crazy. All right, everybody. It's been an absolute pleasure hanging out with you. I've been playing a lot of dominoes lately. Like Mexican train dominoes, or what kind of or like the one where you just knock them over? I enjoy a good domino game. No, like you match the number of dots. Have you heard of Mexican train dominoes? It's a fun. That's the only version of dominoes I've played, actually. I don't even know what the regular dominoes is. Yes, spinny. Yeah, it's fun. That reminds me of summer. Dominoes, like, I feel like my family would get together on the 4th of July. That would be one of the games we played. I know. It's very intense, so you have to prepare yourself. You have to make sure you're ready. All right, everybody. You have a fantastic Monday. I look forward to every time I see you. And I'll see you again on Wednesday. Actually, I have office hours today, but I didn't put up a homework, so I'll be there just in case. All right, adios.